Bonjour tout le monde. Donc aujourd'hui, on a le plaisir de recevoir Scott Armstrong du Courant Institute, qui est pour un an l'IHES et qui va parler d'anomalous diffusion for passive scalars by monofractal homogenization.
So thank you. Thank you for the invitation to speak here. I'm going to be speaking on a joint work with my colleague, Jacques-Louis. The preprint is not available yet, so I'm sorry. You have to wait, but I'll try to hopefully make this talk enjoyable anyway. It's going to be about anomalous diffusion for passive scalar equations using homogenization methods. So let me jump right into it. So the equation I'm considering is this one. This is like a heat equation with a drift term that is very important that this vector field here, B dot the gradient, so B is a vector field. It's important that the vector field is divergence free. So it's, in space, it's divergence of 0. It can depend on time, how it likes, but in space, it's divergence free, so it's stirring. And we think of this, there's a parameter kappa in front of the Laplacian, and we think of that parameter kappa as being very, very small. Okay, so we want to send that to 0, or just anyway, 10 to the minus 12. And we want to understand the behavior of solutions of this in the case when the vector field is also rough. Okay, so the vector field needs to be rough, but also not that rough. Okay, so the vector field, you should think about this vector field as being somehow polar continuous, but not Lipschitz, but definitely at least continuous. Okay, this kappa we call the molecular diffusivity, and we're going to have other diffusivities appearing. So remember the kappa, the small diffusivity that's really from the model is called kappa. Okay, and this equation is typically called, or I found out that it's called the passive scalar equation. I would just call it an advection diffusion equation or a heat equation with drift, but they call it the passive scalar equation. And it should be called the passive scalar equation when the vector field is a solution of Navier-Stokes or the solution of Euler or something. But I'm going to be a little bit more lax about that and just call it the passive scalar equation when the vector field is divergence free. Okay, so this is the setup. And let's see, the inverse kappa is called the Peclet number, which is like the Reynolds number, but this is not Navier-Stokes, so it's called the. So, all right, so this is what I want to study. It's the first thing that you should do, of course, is you should write down the basic energy estimate. So let me remind you what happens when you write down the basic energy estimate for this. You write down the square of the solution, you take its time derivative, you integrate only in space, not in time, and you see what happens. The 2 comes down, it makes a time derivative, you replace it with the operator, and you discover that the advection term dies because it's divergence free. Okay, so you have essentially the same sort of energy dissipation equality that you have for the heat equation. And in particular, the decay of the L2 norm of the solution, I can time integrate this, of course, and you can see that the decay of the L2 norm of the solution is the same as this sort of energy dissipation term. Okay, and we're interested in we're sort of interested in how big this quantity can be. It's at least bounded, by the L2 norm of the solution. It's got to maintain equality here, and this number is the only positive one, so it's bounded by that. Okay, all right, so what does it mean, anomalous diffusion? So of course you can think about this equation like a probabilist, and you can forget that it's a PDE, and you can imagine that you have a diffusion with square root of kappa times Brownian motion, and maybe square root of kappa divided by 2 or something, which is being forced by a divergence-free drift, and you can ask about where the particle goes. And so that's why this phrase anomalous diffusion, so that's why the word diffusion is here. And so what is anomalous diffusion? It means that if we send kappa to 0, maybe your equation has a property that as we send kappa to 0, this sort of energy dissipation term does not go to 0. So that would be anomalous diffusion. If everything would be smooth and the solutions of the transport equation would be unique, which there are sufficient conditions for that, which you know better than me. I don't know the sufficient conditions, but certainly if the vector field would be Lipschitz in space, then the solution would converge to a unique solution of the transport equation. And then you can pass kappa to 0 in the equation, and you would see that you have to converge. So this term should converge to the sort of gradient of the solution of the transport equation squared, but there's a kappa there, so that should go to 0, and it should go to 0 like big O of kappa. But maybe the vector field is not Lipschitz, in which case maybe this number is not going to 0. Yes.
The question, can you turn back to the issue, the first one? Yes. It seems to me that you have the wrong sign when you intervention method.
Probably, yeah. I don't know. Did I put the minus sign? This morning I tried to fix all the signs, but maybe I screwed up. I don't know. I don't know, it looks okay. Oh, you're saying that this is supposed to be, yeah, I forgot to change that sign. But that's 0 anyway, so I didn't check that one. Yeah, thank you. Okay, I have an alert audience here. I gotta tread carefully now. Okay, so anyway, anomalous diffusion may refer to the situation in which the sort of energy dissipation here is not going to 0. And you would really have anomalous diffusion if you could lower bound it by a positive constant times the initial L2 norm of the initial data. Okay, and ideally, so this is what people believe should happen in fluids, right? So that's the point. So you can ask mathematically, does there exist a continuous vector field exhibiting anomalous diffusion? If the vector field is somehow not continuous, you can build examples of anomalous diffusion, but it's kind of cheating. So I'm gonna at least demand that they be divergence free and continuous. It turns out this is open. Okay, so this is an open question, and I think it's an interesting open question. So let's talk about why. So the main idea in Kolmogorov's theory of turbulence, or there's many main ideas, but sort of one of the main ideas is that what happens in a turbulent fluid is there's some energy input onto sort of large scales. So you have some stirring on the largest scale, and then somehow the energy on the large scale goes into scales which are slightly smaller, but then again slightly smaller, and again and again and again, until the energy goes all the way down to the scale at which friction turns things into heat. And so energy is lost, and that happens no matter how small that small scale is, which is in terms of this parameter nu for the Navier-Stokes equation. Okay, and so what that means is that if you have a very small parameter nu in the Navier-Stokes system, and there's some kind of force acting only on large scales, so some kind of stirring on only the largest scales, you should expect that the energy dissipation stays of order 1. Actually, maybe it's just log of nu or something, but let's forget about that. So it should stay of order 1 even for a nu very small. And this is called an anomalous dissipation of kinetic energy. And it's analogous to the anomalous diffusion for the scalar equation that we're talking about. So physicists think that this is an obvious fact, and or maybe this O of 1 should be a logarithm or something, but otherwise it's logs are basically bounded on there's only 12 scales. So, but the physicists think this is an experimental fact, and it's called the zeroth law of turbulence. And mathematicians can't prove anything. We can't even make an example, much less prove a robust sort of theory that most solutions do this in a statistical sense or something like that. Okay, so we would like to talk about that. So let's see. So what did I write on the slide? So yeah, so the motivation is that this passive scalar equation is first of all a simplified model for this, or it should be like the Navier-Stokes equation. I just decoupled the vector field that is sort of transporting things from the solution, right? In the Navier-Stokes system, the vector field is the solution, and they're coupled, and that's very complicated. Here, I'm allowed to pick my vector field, and I just want to study now a scalar equation, which should in principle be simpler. However, it should exhibit the same kind of phenomenon. I mean, if we think that this is what's causing turbulence, yet we're lacking a single example of advection putting small scales into solutions, that seems very bad. So we should at least try to find one example. Also, passive scalar turbulence is interesting. You may want to study pollutants moving around in the atmosphere. There's a lot of reasons why this is actually a fundamental question in its own right. And there was a sort of a parallel theory of turbulence for passive scalars developed in 1951 by Korsun in the US and Abukov, who I think was a student of Borov in Russia. They did the same thing at the same time independently. And basically, you have a parallel theory of where you have all of the same scalings that Kolmogorov derived for the Navier-Stokes equation. Okay, so for example, here's a paper of 2 of my late colleagues who both recently passed away, Marco Avellaneda and Andy Maida, talking about the passive scalar problem. And they worked on this a lot in the late 80s, early 90s. And I'm sorry, I shouldn't have put this in this color, but this is a cut and paste from a paper that they wrote, kind of a survey article. And they're explaining how you can think about the problem and why it's hard and why it's interesting. Maybe I'll skip the slide. So they claim it's fundamentally important. It's not just a simplified model. And they say it's hard because there's infrared divergences. This has to do with where you cut scales off, and that you don't have a good separation of scales. So I'll come back to that in this talk. So let me talk about what is known. And I don't know, there's a gigantic literature on this that spans decades. So I'm really sort of in the danger zone here. So please don't start throwing tomatoes if I forget all the references, but here's how I think about it. So there's something called the Kreitman model. which is a particular vector field B, which is constructed randomly as a stationary random field. It has white and time noise. Okay, so it's just completely white noise and time. And it has some correlations in space, and there's a parameter in the model that you can tune. And what's nice about this model is it, as Krajinen observed, more or less, is that it allows exact calculations. Now, Krajinen was more of a physicist, so he didn't actually write proofs, but eventually Bernard Gawedzi and Kupianen wrote proofs and derived anomalous diffusion for this particular Krajinen model. Okay, and this is essentially the only convincing model that looks anything like turbulence, as far as I'm aware, but it comes from exact calculations. There's ways in which the model is not very convincing because the vector field is white in time. And I sort of insisted that my vector field be continuous, because if you have a vector field that's white in time, I mean, think about it from the point of view of the particle diffusing. The vector field is a drift term, so it kind of pushes the particle. And if you make it white in time, you can kind of kick the particle around and you can say, oh, look, it looks like Brownian motion, it's diffusing. Well, yes, because you are sort of bombarding the particle with a vector field that's so irregular and random that you'll have diffusion.
Yes. Does it mean white in time?
No, it's literally white noise in time. So it's a distribution value. Anyway, there's many rabbit holes that you can go down. I can try to explain more after, but anyway, or you can open their paper and see what it means. But it's a stationary Gaussian random field. Okay, so number two, more recently, there's a work Ribas, Elgindi, Iyer, and Jong. So their paper came out in 2019. It was, I think, published last year, and they have a very interesting example. It's the first deterministic example of a vector field which is continuous in space and exhibits anomalous diffusion. Okay, and the way that their example works is the
L1 is allowed jump in time.
Yes, I'm coming to that. So it's almost Lipschitz in space, and it's L1 in time. And the way that it works is they pick a singular time, say time 1. And they chop the interval from 0 to 1 into dyadic intervals, which get smaller and smaller and smaller at the final time. And on every interval, they make it a shear flow, a periodic shear flow. So just a vector field which does this. Okay. And then on the next time interval, the vector field, it may turn in the other direction, and then has a smaller period and a larger amplitude. And it continues like that until at the final time it blows up. So you're kind of creating a blow up time. And in the limit as kappa goes to 0, all of the sort of anomaly happens at the final last, okay? But it's a very nice example because it is, and they're building on work due to Italians and other people who study these kinds of, what happens, like how do you make irregular vector fields where strange things happen to the solution of the ODE or the transport equation, okay? Now I'm worried that I made an edit to this slide that disappeared, but yeah, or maybe it appears on the next slide. So there are some more works that happen. There are some more works that came based on their work due to Maria Colombo and Sorella. And also, I think Camilo de Lelis and Elia Brue have a paper that's sort of related, but it goes back to their idea and they build on it. I thought I had a slide on that, but maybe it comes later. Okay, so now there's other works. There's works by Bedrosian, Blumenthal, and Punch and Smith. They don't really prove anything about anomalous diffusion. I put them on here because you may think, why did he not talk about them? But they prove other things. So their results are to be understood as treating the Plotchian term as a perturbation, really, of the transport equation. And they're interested in proving things about mixing. Okay. They also have a paper where they talk about anomalous diffusion, but there they have a white noise or sort of random forcing on the right-hand side. And for my purposes, that's cheating. Okay. There are many works on enhancement of diffusion. So what does enhancement mean? How does that relate to anomalous diffusion? Enhancement of diffusion is where you have a vector field that's maybe completely smooth and periodic and divergence free, and you study the equation and you think of it as a homogenization problem. So you zoom out and you make an effective equation, and you observe that the homogenization or the effective coefficients of that effective equation have larger diffusivity. The matrix has gotten bigger due to the effect of the vector field. Okay, so the stirring of the vector field increases the A bar, the homogenized matrix. Okay, so that's called enhancement, where you see that sort of you have two scales and you zoom out on the larger scale and you see that the effective diffusivity is larger. Here, Anyway, there's really a lot of works on this. Here, though, we're asking that in the limit of small diffusivity, the sort of effective behavior is of order 1. Okay, so the anomalous diffusion is and there's lots and lots of works on mixing. Now, how does mixing relate to this? Well, mixing is about how that sort of ODE, the flows of the ODE solution mix. You start with some smooth initial data, you flow according to the transport equation, and you want to see how mixed up the data gets. Okay, in the sense that the negative Sobolev norms decay, maybe the H-1 norm decay. So there's tons of works on that, and that's somehow related to what I'm saying, but it's not what I'm saying. Okay. So what would we like to say? Like what is not cheating? Okay. So we would like to prove anomalous diffusion when V of X is a solution of Euler or Navier-Stokes. Okay. Yeah. So we're not going to do that. So instead we're going to relax our ambitions, because right now we have no examples at all. So at least before we can try to make a solution of Navier-Stokes, let's try to understand some examples. But we still like our vector field to be kind of fluid-like. So we're going to ask it at least be continuous in time, so there's no kind of bombarding the particle back and forth very quickly and getting diffusion that way. And we'd also like it to be a holder in space, partially because if you have a rough enough vector field, you can kind of create things artificially. So a fluid should be holder continuous in space, so we want that. We would like it to be holder continuous in time as well, but at least continuous in time. Okay. And we would otherwise like our fluid to resemble a turbulent flow as much as possible. So we would expect, for example, that our vector field would have many, many, many scales, like infinitely many active scales in it. It's not just going to be a vector field with one scale. So the way that it'll be just holder continuous is maybe it'll be an infinite sum of things which are active on smaller scales, and which when you sum it up, the Lipschitz norm blows up or something. Okay. So now let me talk about Korsakoff predictions for passive scalar turbulence. Like, what does the theory say? I'm in a little bit of danger zone here because I don't know if the physicists would like me calling this Korsakoff. I'm a little unclear on that, but just for a mathematician, here's some minimal predictions that we could get out. There's a trade-off between the regularity of the B and the regularity of the passive scalar, and if their combined regularity goes above a threshold, you don't have anomalous diffusion, because you can just integrate the ODE just like you can if the thing would be Lipschitz. So you can relax the Lipschitz criterion on the B as long as the scalar theta has some regularity to make up for that. And the way that it works is that if the B is C0 beta, okay, and the scalar is in C0 alpha, and 2 alpha plus beta is bigger than 1, you can't have anomalous diffusion. Okay, and this is the result of Constantine and TD from 1993, which is the paper where they proved the easy side of the the Onsager projection. And so that their proof, if you write it down for the passive scalar, it involves these. You convolve the product and compare it to the product of the convolutions and stuff like that. Then it just says it makes this prediction. In fact, if you write it down, you can get a power of kappa. So you see that I said that when beta is 1 and alpha is 0, this should be of order kappa. It should be 1, and so I hope it is. Wait, no, it's not. I may have written these exponents down wrong. Okay, so I'm worried there's a typo here. But the point is that if the irregularity is above this threshold, then this thing should go to 0 with an explicit rate that's positive when this is bigger than 1. Okay, and this is, oops. Wow, I really jumped back. Okay, and this is the result. Let me see if I can use this device. This is the result. Okay, so here is the theorem that we proved. Now this is kind of funny. I wrote 2022. I should update that to 2023, and hopefully I won't have to update it again. We're trying to write down the finish writing the proof, and it's taking a very long time just because the technicalities are large. So here's the theorem. So pick any beta you want between 0 and 1/3. So we can go almost up to 1/3. We can't get on top of 1/3 because we need a little bit of room to do analysis. And pick an alpha that's all the way up to that range. Okay. Then you can find a vector field B which is Holder continuous in space with beta and in time with beta, but you can't have them both at the same time. I mean, you have Holder continuity in space and time where the exponents add up. And there's a sequence of kappa n's, not the full sequence, but there's a particular sequence which goes to 0, as in goes to infinity, such that for every initial data, which is, say, mean 0, the solution of this equation, two things. You have, sorry, this is purple, I don't know if you can see it very well, but this says that you have anomalous diffusion along that subsequence of kappas, okay? And this one says that the bounds for the scalar are what you would think. These scalars are uniform in that Holder norm, okay? So these are the two results. So you have anomalous diffusion and you have Courson-Abunkov type Holder regularity. So I should say again that I was talking earlier about this result of Drivas, Elgendi, Iyer, and John. They made an example of anomalous diffusion. Colombo, Crippa, and Sorella took their example and then mixed it with some very nice convex integration techniques. And they proved also a bound on the scalar, basically for their example or a similar example. Okay. So this result about having a sort of scalar bounded, at least when the vector field is rough in time, has now since been proved by them. However, they only have it for a single initial data because they use convex integration techniques. Okay, so this is the result. The proof will be between 200 and 300 pages, so it's taking a long time to write down because you have to prove very delicate estimates and you have to propagate them down infinitely many scales. So it's taking a long time to finish writing it. But let me try to explain how the proof works to try to give you an idea. It's one of those proofs where the idea is fairly simple and then the implementation is where you spend all your time. Okay, so this result, as I stated, was for d equals 2, but d equals 2 is not needed. The only reason that we use d equals 2 is because we like to write divergence-free vector fields as the grad perp of a scalar. And in higher dimensions, you would have to write it as the row divergence of a skew symmetric matrix. And that's annoying. And so we just do 2D, but everything works for higher dimensions. Our vector field has what we call a monofractal structure. So it's fractal-like. There's a base fractal, and we put wiggles into the solution in a fractal-like way. And in particular, there's a sequence of active scales. We build a sequence of active scales into the problem. This sequence is explicit. There's nowhere in the proof of this theorem is there any appeal to any soft limit by compactness. Okay, so everything will be explicit and computable. Our constants, in fact, when Vlad writes the lemma, the constants are explicit, like 2 to the 18 and stuff like that. But so everything is completely explicit. The reason for the sequence of kappas and not having the full kappas is we need that the kappas. So when you have a kappa, it gives you a length scale at which the Laplacian is going to make things go away to heat, right? In which this is the inertial scale or something. And you need that kappa, the length scale that corresponds to that kappa, to correspond to one of the scales you put in your vector field. If it's in between two scales of your vector field, we don't know what happens. But if it's close enough, maybe by a factor of 10 or something, to one of the scales we put in here, then it's okay. The solution will have a monofractal structure. Okay, so we have to basically, this is one of those theorems where in order to prove the theorem, you almost have to write a formula for the solution. Like you can't lose anything in an estimate anywhere. And so because of that, as a side product, we understand the solution very, very well. And it has a fractal structure. In fact, the scales that are in the solution, as you let beta go to 1/3, correspond to, you can read off all the scales that are predicted in Kolmogorov turbulence or whatever. You can find the Richardson 4/3 law and all kinds of stuff like this. The smallest active scale for this thing is this guy. This is the smallest active scale for the scalar. The scales below that are smooth, and that's what you would predict by the Courson-Abunkov theory. And okay, if you let beta go to 1/3, you get all the other scalings. Okay, so comments on the proof. Yes.
For the sequence Kn, do you have some restriction, or for a given sequence which is going to 0, you can build also?
No, I can't do that because I need the sequence. Yeah, so the sequence going to 0 needs to correspond to my active scales. I can build my active scales in a sequence, but a sequence can't be, it needs to be super geometric. I need to get some spreading of the scales as I go down, which is non-physical, but is mathematical, okay? So you need a tiny bit of, all right, so the sequence of active scales What you'd like to do physically, so you have this epsilon m, which these are the epsilons that are getting smaller and smaller. You would want these to be 2 to the minus m more or less, right? Just sort of geometric. You can't do that because the proof breaks. So you have to make it slightly worse than that. And so what you do, but if you make it slightly worse than geometric, you're doubly exponential, right? So you have to do something like, so the smaller scale is the scale that came before to a power q, 1 plus q, and q is some tiny number. Okay, and that gives you some double exponential thing. So it's not geometric, but so I would need your kappas to be doing that basically, because the kappa is related to epsilon through some numerology. It's the epsilons to this power. Okay.
And having the equality is not enough. Like if you have a given sequence, you can, so if you have a, say, epsilon m, you cannot take epsilon m plus 1 to be the next item in your sequence, which is small enough. You actually need to have that equality here.
No, I don't need that.
Oh, okay.
No, I don't need that.
So
That's just this is a squiggly thing here. Yeah.
Okay. Okay.
I just like, because everything is quantitative, you can perturb things like that, but you can't perturb things that break the proof. Yeah. Okay. So I'm not using like exact computations that rely on this. I just need this to be approximate. So comments on the proof. First of all, do not think that this is a perturbation of the transport equation. We are not saying that if you look at the transport equation, you can treat the Laplacian term as like a tiny perturbation, and this reduces to like chaotic properties of the Lagrangian flow. That's not what we're saying. We don't believe that. And we think that's the wrong way to think about the problem. Indeed, we believe that at every scale, the equation properly renormalized looks like an advection diffusion equation with everything in balance. Okay, so what happens is you go down, if you zoom in on the equation and you go to the smallest scale, the inertial scale, there you'll find a balance between the advection term, the B, the drift term, and the diffusion term. They'll be in balance by definition. If you look at what's happening on that scale, you can think of all the scales above as kind of this, slow scales, and you can kind of try to understand just that scale. And you can apply homogenization idea to say, okay, I am going to homogenize this, and I'm going to get an effective diffusivity. And so you go up a little bit in the scale, and you homogenize away the fast scale, only the fast scale that you're on, and you since erase that scale from your vector field, and you increase the kappa. Okay, and then you iterate that, and each time the kappa increases a little bit, and you iterate that all the way up, all the scales, until you get to the top scale and kappas of order 1. So that's how the proof works. When we thought of this idea in like the second day we were working on the project, and we thought we were very clever, and we thought that probably no one had ever thought of this before. And then we started to look at what was in the literature, and we kept finding sort of this idea, was here, was there. We couldn't find where it appeared first, and so finally it appears to go back to 1851. So it may be the oldest homogenization. The appearance of homogenization somewhere was 1851, but I think Boussinesq was really the one that articulated it. In the fluids community, they call this eddy diffusivity, and they refer to the idea that I'm talking about as, well, they call it the eddy diffusivity method, and they call it a renormalization group method, things like that. Okay, so if you look in the book of Landau and Lifshitz, they, of course, it's heuristic, like all heuristic derivations of Kolmogorov's theory, but they will use this sort of picture, this renormalization upscaling of the problem to derive Kolmogorov's turbulence. Okay, and we're going to try to formalize this using homogenization theory. So this I already said. So this slide is just saying at every length scale we normalize the problem or that is we homogenize the problem, and we see the advection diffusion term, the advection term gradually adding diffusion. The one feature of the proof that's funny is that you have to prove the regularity of the scalar together with the anomalous diffusion. You don't prove them separately because you need the regularity of the scalar to help your homogenization estimates. Okay, and this I already said. So the vector field has a self-similar monofractal structure. And this I was saying here in the blackboard, the scales are supergeometric, not geometric like they should be physically. Scales in physics, of course, communicate across one order of magnitude at a time, not a giant, they don't make giant leaps, but we have to do that to make our proof work. Okay, so now let's see. So now I can try to get through some of the ideas of the proof. But are there any questions right now before I switch? Yeah. Oh, you were giving me the all is okay. Okay. All right. So I want to back up and talk about homogenization and enhancement really quick. So I can kind of, in some sense, almost give a heuristic proof of what's going on here. So suppose you have a B of t in X, which is periodic and again solenoidal. Then you can, so you're in dimension D now, you can find a skew symmetric matrix. So I think for this, you also need B to be mean zero. I forgot to write that, but B is also mean zero. So you can find a skew symmetric matrix such that the row divergence of S equals B. So this is the sum, it's there in coordinates. This allows you to write the drift term as a term that looks like an elliptic guy, but it's skew symmetric. And this allows you to write the whole equation as just a second order operator like that, but the matrix in there is not symmetric. Okay, so this is the reason for studying homogenization of non-symmetric, elliptic or parabolic equations. Okay, all right. So the point is that, and actually, one should probably not write this term and just write the equation like this in the first place, because thinking about this thing and how it behaves in your homogenization problem is actually maybe gives better intuition for what's happening. Anyway, this is what you can do, and then you can show that if you homogenize this, you'll get some equation, or sorry, this is the equation. We can call this A. And if you zoom out and you take a homogenization limit, you'll find that the homogenized matrix for this guy is bigger, strictly bigger than kappa times the identity, or it's only equal to kappa times the identity if somehow this is not doing anything, like if it were zero or if it's kind of a degenerate in the problem. Okay, so homogenization says that this operator will converge to something, some A bar, where A bar is the effective diffusion matrix. And again, the skew symmetric part causes enhancement. Okay, and you can see this, you can prove the enhancement in like 3 lines. What you do is you take the corrector equation for each problem and you compare them. And you see that the corrector equation for the guy with the skew symmetric matrix has more energy because the other guy is kind of, the symmetric equation is energy minimizing, and therefore the other one has to have more. So this formalizes the idea that stirring increases the diffusivity experienced by a particle. Let's take an example. Here's a cellular flow. So here the arrows are easy to see maybe from the back, but here what's going on is that the vector field is stirring in circles like a little eddies, okay? And here they go, what is that, clockwise, and here they go counterclockwise, and they line up in like a checkerboard clockwise, counterclockwise pattern. This is a famous example that a colleague of ours, Steve Childress, analyzed in 1979. And basically, it was, so he derived that if you homogenize this, then starting with kappa, then you would get square root kappa. In fact, you would get a particular constant times square root kappa plus little o of kappa, or square kappa. And then this was proved again by Papanikolaou in 94. I think I got the names out of order. It was claimed that Childress's argument is not rigorous, but actually when you look at Childress's argument, it's rigorous. So I don't know, but anyway, this is what happens. And you can see heuristically why. There's like a little physicist proof in like 2 lines for why. Here's what happens, okay? So say that your kappa is very, very small, okay? When your kappa is very, very small, you're going to spend most of your time doing what the vector field says. You're going to spin in a circle. Okay, but occasionally you'll get near the boundary of these 2 little cubes, and then the diffusion may move you across to the other side, and then you'll find yourself spinning in the other cube. So when you're in this boundary layer, and the boundary layer has thickness square root kappa, what you do then is you basically do a random walk on the actual like lattice with speed 1. So you're in, because the invariant measure is equal to 1, there's the particles, it's divergence free, so it's not going to bunch up the particles. So basically you spend kappa square root fraction of your time doing a Brownian motion with variance 1, and the rest of your time doing nothing. So you should be of order square root kappa, okay? So that's what happens in this example. Notice that you don't get up to 1. You get square root kappa. You don't go all the way to 1, okay? Here's another example. Here's a shear flow. These guys are going down. These guys are going up. It's just shearing, okay? This is a more dramatic example. Now, in this example, I'm going to go ahead and say that the length scale is epsilon. because I don't want to, I want to scale this down eventually. So the length scale is epsilon. What happens here in the sort of physicist particle point of view is the particle, whenever it's in one of these channels, it basically goes up with constant velocity. But the diffusion will move it in the horizontal direction a little bit. Eventually, it'll switch into the other channel, and then it'll go down, right? So it's basically doing a random walk where it goes up for a long time, and then at some random time switches, and then goes down for a long time, and then it sometimes switches and then goes up, okay? Now, what is the switching time? Well, you're typically in the middle. So how long will it take to switch over? Well, the amount of time it'll take to switch over is, I didn't write it out. No, I didn't write it on the slide. Okay, it's going to be proportional to 1 over kappa squared, right? Or something like that. Or no, it's the length scale squared over kappa. So it's going to spend epsilon squared over kappa amount of time before it switches. And that's the distance that it's going to move. So its steps are of that size, and the time scale on which it takes those steps is, what did I say, epsilon squared over kappa, I think. And so what you get is, you get more diffusion if you started with less kappa. The effective matrix will have a huge amount of diffusivity in the up-down direction, and it'll have more when kappa is smaller, okay, because it makes the steps bigger. It takes a longer time to switch. Okay, so you have this effect, is kappa plus 1 over kappa, okay? And it scales like epsilon to the 4th, and rho is for me is the strength of the vector field. It's the magnitude of the vector field. So it's the square of the vector field times the 4th power of the length scale divided by kappa. Okay. And if you alternate the flows in time between up, down, and left, right, maybe with a smooth cutoff so it stays continuous, you'll get something like this, where you can have again a diagonal matrix, but it'll be much, much bigger, proportional to 1 over kappa. Okay. All right. So I got me speed up now. So, okay, so here's a picture of, it's not a very good picture, so let me skip it. Yeah, so the diffusion is going to enhance. The new diffusion in this picture is the old diffusion times the square of this parameter, which is rho epsilon squared over kappa. Rho is the strength of the vector field, epsilon is the length scale, kappa is the old diffusivity, okay? And this number here in red is a dimensionless number, and that's actually the ellipticity contrast of the problem. If you're doing the homogenization problem, it's the contrast of your matrix, okay? And so this thing is going to homogenize with this new kappa on spatial scales larger than this ellipticity contrast times the old epsilon, and on time scales larger than this, the time scale is the inverse Lipschitz constant of the vector field, times again this parameter, okay? So it's very important in our problem that because we build the scales into the vector field, we don't have infinite scale separation. There's no like typical homogenization limit where you make the scale separation go to infinity. We have a finite number of scales. They're not being stretched. So we have to prove homogenization with an error, and we have to be able to add up all the errors and still not have very much across infinitely many scales. So it's very important that we know that our homogenization is finished before the wiggles from the next scale get put in, okay? So we have to have this intuition of what scale homogenization, and this happened. So here's the idea for building our vector field. What if we make a vector field, which depends on time, and depends on just an infinite sequence of scales, okay? So we're going to choose these scales. Scales below inverse square root of kappa don't, that's bad. That should be not with a negative there. Scales below kappa 1/2 do not matter. So there are not exactly kappa 1/2, but kappa to some power don't matter. So there's some smallest active scale epsilon n, which depends on kappa. And we're going to homogenize this operator here with epsilon n, okay? And we're going to show that it homogenizes to, so we start at the bottom. It homogenizes to some kappa bar n. I'm going to make my sequence of kappas descend. So the first kappa I define is kappa bar n, and then I define kappa bar n minus 1. And what's happening here is now the scale's gone, okay? And we have enhancements, and then we have a new equation with a new kappa and a new thing, and then we just iterate that, okay? So for every kappa bar sub m plus 1 times Laplacian plus a d, which stops here at epsilon m, we homogenize it, we get a kappa bar m. Now this guy doesn't have that fast scale anymore, and we have that, okay? Yeah.
And the vector field B at different scales looks the same.
Yeah, so we'll get to exactly what the vector field B looks like. I'm gonna try to hurry now, because that's the fun part. Okay, so here's how we build the. Okay, so maybe I skip this. Okay, so anyway, I'm gonna make, so my epsilons are a sequence of active scales in my vector field. They go to 0 faster than geometrically. I have a sequence of shear flow Lipschitz constants. This is the strength of the vector field. And at scale epsilon m, this B is going to look like an alternating shear flow, which does not depend on time, okay, with these parameters. And then if you look at the formula I wrote for the effective diffusivity, you see that your kappa m should satisfy this recurrence, okay? And then you have to see if that recurrence gives you something. And it does. You're allowed to choose the Lipschitz constants to be epsilon to the beta minus 1, where beta is any number less than a third, so that the Lipschitz constants will blow up, and this is consistent with the C1/3 scaling. And these will be satisfied, and then this will allow this to happen, because the reason I need this form, so this is kind of my recurrence relation in my renormalization, and this one is the condition that the scale by which the previous guy has homogenized is less than the next scale. That better be true, otherwise it falls apart, okay? And this constraint turns out to give you the 1/3. That's where the 1/3 comes from, okay? So you can check that if you choose this sequence of epsilons, then it works. There's a whole bunch of horrible movement, and I wrote this in red. And what you see is the kappa m is epsilon m to the 4/3 plus a tiny constant, and that's the Richardson 4/3 law that says that at this scale, the sort of eddy diffusivity on that scale behave like the scale to the 4/3. Okay, so here's how we build it. Finally, here's the fun part. So you start with naive idea number 1. You're just going to let your B be the sum over the scales of your U M L X. M is the scale, and U is a shear flow on that scale, and L is just there, so I can put this cutoff function in here in time like that, which interpolates between horizontal and vertical in some nice way. It's switching back and forth so that my diffusivity matrix is still diagonal, which I will need. Okay, so this is the explicit U. I'm sorry it's in red. That's what you think you're going to do, and you think that's going to work. That does not work. The reason that doesn't work is very simple. All of the examples, so when I've been discussing it before, I've had a time-dependent vector field, and my examples have been non-time dependent. Okay, that's the reason why you need a time-dependent vector field is that if you try to put many scales in your vector field, the big scale will kind of rub out the small scale, because remember, you're trying to make a vector field which is continuous, so the amplitude of the small scale should be smaller. And if you make a little shear flow with an amplitude like this, but then there's kind of a background flow which is much larger, you'll erase the enhancement. You'll have basically no enhancement. And so the whole picture is destroyed. And so you think for 5 minutes and you decide, but how can I do that? I mean, I'm making like I have a shear flow and I want to put little shears on top of that shear. But maybe if I let the little shears flow down the river of the big shear, then it would work, because in the coordinates obeyed by the sort of trajectories of the big flow, the little flow looks stationary again. So that's what you do. You do this exact thing, except at every scale, instead of using U here, you compose U with the Lagrangian flow from the previous version of B that you just defined. Okay. So the real way to do it, okay. So did I write it? Yes. So you take your B, so you define a sequence. B0 is just one shear, okay? Then you take X to be the flow of the Lagrangian flow, and you take your U and you compose with the inverse Lagrangian flow. This basically says that the scale you're putting in is being transported by the larger scale. So the larger scale has no effect on it. It doesn't even know that it's there. And so these things can homogenize independently. This is a feature that our model has that, by the way, the Crichton model and basically all other models don't have. And we think it's essential for the whole anomalous diffusion process. So yeah, so this ensures that the background vanishes. Note that real fluids do this. If you have a solution of a fluid equation, the high frequencies are transported by the low frequencies. That's what the equation says. Okay, so in order to make our proof work, we had to accidentally make our thing look like a fluid. Okay, it turns out that putting this in here causes gigantic headaches, because then you have to, this thing will fall apart on the inverse Lipschitz time scale of the previous guy. And so you have to cut off and then restart the flow over and over again. And you have to put in a million time cutoff functions, so you have 2 layers of cutoff functions. And it turns out that every time you have a time cutoff function, the time cutoff function has to vary on time scales that are larger than the scale on which the shear flow is homogenizing. But then the changing time actually creates wiggles in time that themselves have to be homogenized. So you have to homogenize like three different things each time you're doing one level, and there's infinitely many levels. Okay, so even showing that this vector field, that these flows and the vector field you get, it has the regularity you think it has, is a funny problem, because if you try to follow the proofs of the regularity of ODE flows in order to get a bootstrap going to prove by induction that your V has the right regularity, you actually have to propagate basically like analytic estimates. So your base fractal has to be analytic, otherwise the vector field you build like this will fall apart. Okay, so and again, we have to refresh the flows on certain time scales, otherwise the thing gets way too distorted and we lose track of what's going on. And so we need that the time scale of homogenization is much less than the scale on which we have to refresh the flows, which is the previous guy's inverse Lipschitz constant. And this restriction is actually the one that makes beta 1/3. I said it was the previous one, but that was a lie. I forgot that I put this on the slide. So it's this refreshing of the flows that causes the 1/3 to happen. And otherwise, what we do is we show that again, like this homogenizes to this. This means that this is close in L2 to that. And the error that we make can be summed over the scales. And so it means that we're going to eventually show that the L2 decay of the original theta is close to the L2 decay of the homogenized operator after all scales have been removed, which turns out to be the heat equation, which we know decays. So that's the proof. And as I alluded to earlier, while we do this, we have to show that the regularity of the theta m is doing what we think it does. And in order to prove this regularity bounds, when we do our homogenization at every scale, the homogenization error estimate has to be at infinite order. So we can't just say, oh, we've homogenized with an error of the scale epsilon m to the 1/2 or something. We have to have epsilon m to the 1 billion, or our proof won't close. So because of these reasons, it takes a long time to write. Anyway, I had more slides, and these are more fun, so maybe I'll take 2 more minutes. So anyway, there's this book of Uriel Frisch that we decided to open when we decided to actually become educated. And in section 9.6, this was funny. This is when we discovered that our idea wasn't so new. He has a whole subsection in which he has, homogenization, a very old idea, and where he describes exactly our proof strategy. He also explains why it'll never work, because really, he says it's only at best a pedagogical device, because you could never actually get the proof to close, because what are the problems? You have scale, you have a finite scale separation, and the mathematical rigorous, homogenization theory needs infinite scale separation. There's no clear separation of scales. It's a very big problem. This won't work. Instead, what you have to do is you have to use renormalization group methods from physics, which, while they aren't rigorous, at least they work. Okay, that's what he says. You have a survey on this equation by Andy Maida and Kramer. Andy Maida tried to feed this. He took it off the shelf. It's like 300 pages, and he almost made me eat it in his office one day. And it took me years to finally sort of understand what was there. He also talks about this anomalous diffusion and renormalization for simple shear models. That sounds like all the buzzwords that we're doing. They also explain that fully developed turbulent flows, blah, blah, blah. Homogenization theory may therefore not be adequate to describe the macroscopic passive scalar dynamics. And again, he says it's because there's a huge range of scales and you don't have scale separation. So the way that we did this is that we put this sort of non-physical extra scale separation in. I mean, any 2 scales are separated a finite amount, and that's not changing. But as you add more and more scales, they get stretched more and more and more and more. And so that the homogenization that comes from these far down scales happens with less error. And that allows us to sum up all the errors. Okay, so that's sort of the idea. And that's kind of not physical, but I don't know how to do it otherwise. But in order to, because we're stretching the scales as you go further down, you're also then not making use of those scales. And you need to use all the scales if you're going to get your enhancement all the way up to order 1 to have anomalous diffusion. So the way that you fix that is you make the vector field slightly stronger, of course, as you go down, more than just the Holder continuity would allow, which is why we're not on top of the exponent of Holder continuity. But when you do that and you rewrite the problem as an elliptic equation, what you have is a high contrast homogenization problem. And so what our proof requires is sort of an infinite order homogenization theory that works at high contrast optimally in the ellipticity parameter. So that's taking a while to write down. We are formalizing that part with Vlad and our PhD student Kiefer, who is there. Anyway, I think that's all. I think I'll skip that and just save that slide. Thank you.
So maybe we'll start with the questions in the room and then switch to the online questions. Are there questions? And maybe Scott, if you can remember it, it's there if you repeat the question from my mind so that people can hear it.
Okay.
Could you explain why, when you have your shear flow, you have to alternate between left, right, and like this?
Yes.
Well, if you only do like this, what is going to happen?
Right. So why do we have to alternate the shears between left, right, and up, down? So when you have down shear, you're going to enhance only in the up, down direction. Okay. And so if you want to enhance in all directions, you need to have both. And you may wonder why not have one scale which is up and the other scale which is down, and or left, right, I guess, and alternate it like that. If you do it like that, then what you're essentially doing is you're giving up half the scales for each direction, and it won't work. Because your up down, the way that it works is the enhancement is the enhancement in the up down direction is inversely proportional to the diffusion in the left right direction. Not for every initial data. Yeah. Okay. I mean, and I don't think I could control the situation if I only had one direction. Like I need it to be kind of rotationally invariant and stuff, because the solution is going to do crazy things. Because I mean, the other thing I didn't say is that we have this homogenization problem and we're doing one scale at a time, but the other scales are still there. And we have to homogenize to infinite order. And those scales are acting like they're making the problem locally periodic, if you want. So we actually have to do infinite order homogenization for locally periodic coefficients. And the derivatives of those scales actually enter into the calculation and affect the correctors and things. And those scales will destroy the symmetry of whatever you're trying to do if you try to do just one direction, I think. I mean, when you do the shear flow, the up-down direction communicates with the left-right direction through the scales. Because if you think about how it works, if you're going up and down in these channels, the time scale depends on this guy's diffusion. So if you're not doing any left-right enhancement, things will fall apart, I think. Yeah. Sorry for that long-winded answer.
Yeah, I had a kind of similar question. So you presented two examples, the ones with the shear flow and the one with the vortices in the beginning.
Mm-hmm.
And in the end, doing the shear flows up and down and then left, right, it's not the same as having vortices, right?
Yeah, so the vortices won't work. And the reason that the vortices won't work is that when you have those vortices, so every vector field that enhances is really a shear flow. It's just, so like those vortices is a shear flow. The only part of the vector field that's causing any enhancement is the part on the edge where it's kind of shearing. And so what those vortices are doing is it's like they're shear flows on the boundary, and they're just, you may as well just erase them in the middle. So they're just not using all their space. In order to have full enhancement, you have to use all the space you're given, and the shear flows do that maximum. And that's why real turbulence is probably not really, it's probably bounded by a log, and not really, because it's not going to use every bit of its.
Well, except if they are not on a grid, no?
Yeah, I mean, of course, we'd like to do a vector field which is random and, to have a genericity in our result, but we can't do that for various reasons right now, at least. But I think that a real fluid is having most of its enhancement in special places at special times. And that's a small volume fraction of the space. And as you go down the scales, the volume fraction of that changes and gets smaller, actually. And this is why this would be multifractalness instead of monofractal. I'm getting myself into trouble here. Yeah, but I think that will cause that. I mean, our fractal example is really the kind of the same at every scale. And I think the real physical example is not actually the same at all the scales. And this is the multifractalness. And so I think that it'll do something a bit different. But if you want to make a mathematical example, you really want to use everything you're given because the problem is hard enough. So you want to fill the space with as much enhancement as you can, and the shear flows do that. Yeah.
As a side result, this optimal rate of optimization for high contrast will be a byproduct only thing.
That's a good, yeah. So that's a good question. So are we, yeah. So the first part, so the result's actually in two parts. And one part is just the homogenization theory, which is infinite order homogenization of locally periodic fields in high contrast. And we have to get the optimal power of the ellipticity in our error estimates for anything to work. And that is going to be done in general. And that's a huge mess. We're gonna finish the proof hopefully this spring, I hope. And then once that's done, then it should fit into, I mean, you know, it fits into the other part. But that part should work in general. I mean, that part should be a general theory. But I think if you didn't have the locally periodic aspect and you just had periodic, it would be much easier. And that you can kind of read off from what's, I don't know, maybe you can. Yeah, I think you can. I think that result's also not in the literature yet. What makes this hard is that you have is the requirement that you do it to infinite order, and the requirement that you allow the coefficients to not actually be periodic, but to be sort of locally periodic. That causes huge problems.
Other questions?
So you said that in the end you prove anomalous diffusion, but in the end you're still using some homogenization technique. So can you describe a bit better the limits of your theta? Like,
I mean, there's no limit because there's nothing being sent to zero, if you want. You mean as kappa goes to zero?
Yeah.
I mean, as kappa, we can show that the theta kappa m and the theta kappa m prime are getting close to each other. But there, you know, if you take kappa equal 3, how do you describe it? Well, I mean, the thing will say that it's close to the solution just of the heat equation with the final kappa bar 0 with error 0.00001. But there's nothing being sent to 0 that can remove that. I mean, there is a scale, which is like 1/50, which has wiggles. And so that scale is not being, that 1/50 is not going to 0. And so there's going to be an error of order 1. The point is that our error of order 1 is less than the amount that the heat equation's L2 norm drops. And so we know that there is some dropping in the L2 norm because our error is 0.001 and the L2 norm dropped by half. So we know that it has to drop by 0.499. That's the point.
This incommensurability of scales that you need for B, is there hope that for these V, if it's Navier-Stokes, that it will pertain in time?
So the question is there hope that you can make V solve Navier-Stokes? I don't know. I mean, the V that we're making, you know, we have shear flows and they're switching directions. And then we're composing with the Lagrangian flows and we're cutting them off and starting and restopping. All this starting and restopping makes it look not like Navier-Stokes. On the other hand, it should make it look like Navier-Stokes with a forcing. I mean, if you take 2 scales and you stretch them, then in leading order, our thing solves Euler. So in some sense, we can make our solution be almost a solution of Euler, except for this cutting off. I mean, until the cutoffs come. So I think Vlad actually wrote some lemma that says our thing is a solution of Euler with a right-hand side forcing term that has such and such regularity. And so it looks like a solution of Euler at leading order. Like I said, it looks like a fluid. Now, I don't know, maybe there's a way to use convex integration methods to make it a solution of in some weird weak sense, or I don't know. I prefer to actually keep it smooth and just see it for what it is, because it's a very concrete example. I mean, it's explicit in some sense.
Okay, maybe the feeling that the construction would say that the one which is done for Navier-Stokes, for one solution of Navier-Stokes, they
Yes.
don't even the one of Vicol and
Yeah, there's no convex integration. Yeah.
There is at the level of the construction, the detailed construction, there is no connection. I mean,
I don't know. Okay, so the question is, what is the connection to convex integration in the building of the solution? So this vector field, in a sense, is not wild, right? We're not trying to make it a weak solution of anything, so we don't have to. So it's just a Holder continuous thing, and you can actually stop the construction at some level, and it's C infinity. We have bounds on all of its derivatives. In fact, we can't prove that the next one is Holder unless we have bounds on all the derivatives of the previous ones, like analyticity estimates. So it's really a smooth function, if you want. And you can, you're allowed to, if you given a kappa, you can rub out the small scales below that scale, and it's C infinity. You can use that. So, but what is the connection to convex integration? The construction itself feels like convex integration in many ways, because we're in convex integration as I understand it. I mean, maybe Vlad would be able to answer this better, but you do put in many scales, and you do put in wiggles, and they even have these time cutoffs. Yeah. So the construction feels like convex integration at some level, even though it's not convex integration. Yeah. And indeed, if you use convex integration, you would sort of need to build the solution to the passive scalar at the same time, and then your construction would only work for one initial data. So the thing we're doing with this sort of renormalization, homogenization argument somehow right now we think can prove more, at least as far as we can tell.
Other questions in the room? No? Are there questions from the online audience? No? Well, in that case, thank you again, Scott.